Okay, so we have finished up our trig chapter in chapter 9, and we've moved on to circles, which is all in chapter 10. And in the first section of chapter 10, we start talking about lines and segments that are going to intersect circles. So the definition of a circle is just it's all the points in a plane that are the same distance from a given point called the center of a circle. So they use this fancy word equidistant. Remember, that just means the same distance. So it's the same distance from the center of your circle. Now, let's just say you had a circle with a center that was labeled A. When they label a circle, like when they name it, when they start talking about it, what they do is they put a circle, they put a dot in the middle, and then whatever that center point is, they label it. So this would mean circle A. So some definitions. A segment whose endpoints are the center and any point on the circle is a radius. So we've got our center here. This is going to be a radius. And then we have a chord. A chord is a segment whose endpoints are on a circle. So it doesn't really matter where the endpoints are, as long as both of them are on the outside of the circle, it's going to form a chord. And then the diameter is going to go all the way across the middle of the circle through the center. So technically a diameter is a chord, but it has its own special name because it goes through the center of a circle. And then we have a couple other lines with our circles. The first one being a secant line. That's going to be a line that intersects the circle at 2 points. So the difference between a chord and a secant line is that a secant line is a full line. It's got the 2 arrows on the end, where a chord stops. So the endpoints, the points on the circle are the endpoints. It doesn't go any farther than that. And then we also have what's called a tangent line. Now this is different than the tangent we had in the last chapter. It's not a trig function, it's just a type of line. But a tangent line is going to be a line that intersects the circle at only one spot. So it's just touching the outside of the circle. That point where it touches the circle is called the point of tangency. So point B would be your point of tangency on that circle. So number 1, we're going to look at the segment, line, ray that we're asked to look at in the diagram and decide, is it a radius, a chord, a diameter, a secant, or a tangent of circle C. So we've got the segment AC first. So that's just this portion right here. So it starts at the center, it ends on the circle, so that's going to be a radius. When we look at AB, we're going from one part of a circle to another point on a circle, and it's going through the center. So that's going to be a diameter. Part C, the ray DE. So we're starting at D, and we're continuing on through E. That only intersects the circle at this point B. So that's going to be a tangent. And then we've got AE, which goes all the way through the circle and intersects at 2 points, which is going to be a secant. So coplanar circles, remember coplanar means that they're in the same plane, and common tangents. So in a plane, 2 circles can intersect in 2 points, 1 point, or no point. Coplanar circles that intersect in 1 point are called tangent circles. So remember, tangent just means that it only intersects at 1 point. So tangent circles are only going to intersect at 1 point. Coplanar circles that have a common center are called concentric circles. So they share the same center point, but they don't intersect at all. So we've got 2 points of intersection, 1 point of intersection, which would be tangent circles, and no points of intersection. So that could be completely separate, like these two circles here, or that could be concentric circles, like these two circles here. A line or segment that is tangent to two coplanar circles is called a common tangent. A common internal tangent intersects the segment that joins the centers of the two circles. A common external tangent does not intersect the segment that joins the two centers of the circle. So what that means is when it says the segment that joins the centers of the two circles, so if we have the center of the bigger circle and the center of the smaller circle, if we join those in a segment, meaning they don't extend any farther, that's going to be a common external tangent. So it's not going to, that segment doesn't touch this tangent here. But when we have a common internal tangent, that segment intersects the tangent. So we've got the center, if we form that with a segment, it goes right through that point of tangency. It goes right through that tangent line. So this would be a common external tangent. This would be a common internal tangent. So in 2, 3, and 4, we're telling how many common tangents the circles have, and then we're going to draw them, and we're going to state whether the tangents are external tangents or internal tangents. So in number 2, those circles are not touching at all. They're not intersecting once, twice, nothing. So these aren't going to have any common tangents. Number 3, we have a common tangent right here. So we're going to have one common tangent. And then if we connect those two centers, they don't intersect the tangent at all. That segment doesn't intersect it at all, so it's an external common tangent. And then in number 4, we have two circles that have the same center, but they don't touch at all. So that's not going to have any common tangents because those are concentric circles. So we have a couple of theorems about tangent lines in circles. The first one is the tangent line to a circle theorem. In a plane, a line is tangent to a circle if and only if the line is perpendicular to the radius of the circle at the endpoint of the circle. So basically, we have a radius here, QP, and we also have a tangent M, and that tangent and that radius always are going to form a right angle. So they're always going to be perpendicular, always going to have 90-degree angle. And then the second theorem, the external tangent congruent theorem, says tangent segments from a common external point are congruent. So we have a tangent here with a point of tangency at T, and we have a tangent here with a point of tangency at R. Since they intersect at this point S outside the circle, they're going to be congruent to each other. So if RS was 10, then TS would be 10. So they just have to have the same exact length. Okay, so number 5 is DE tangent to circle C. So remember, lines are tangent if they only intersect at one point, and if you're not sure, the radius and that tangent line have to be perpendicular. It has to be a right angle. So in this case, we just have to figure out, is that a right triangle or not? Well, our radius is 3, DE is 4, and then from this point on the circle to E is 2. Well, from C to that point on the circle is a radius. If this radius is 3, this radius has to be 3, which is going to make this whole side CE 3 plus 2, or 5. So remember Pythagorean theorem, your biggest side has to be C, or across from the probable right angle. So that's going to be 5 squared. And then our other two sides are A and B. So 3 squared plus 4 squared. We need to know if those two sides are equal. So 9 plus 16, is that equal to 25? 9 plus 16 is 25. So the two sides are equal. So it's a right triangle, which means DE is tangent to circle C. And then in number 6, they're telling us that ST is tangent to circle Q, and they want us to find the radius of circle Q. So we know that QS and ST are perpendicular, so we've got a right triangle, radius of R, from this point on the circle to T is 18, so that whole side is going to be R plus 18. That's our hypotenuse. So we're just going to set up Pythagorean theorem. So R squared plus 24 squared is going to equal R plus 18 squared. So when we start simplifying this, so on the left side we have R squared plus 576. Now on the right, that R plus 18 squared, remember you cannot just distribute that square, because that's the same thing as having R plus 18 times R plus 18. So we have to FOIL that out. So R times R is R squared. R times 18 is 18R. 18 times R is another 18R. 18 times 18 is 324. So we combine our like terms on that side. 18R plus 18R is going to give us 36R plus 324. So we need to get our common things together. So R squared and R squared. If I subtract an R squared on both sides, it's going to cancel out or subtract to 0 on both sides. So I've got 576 equals 36R plus 324. Well, now it's just a regular equation. So if I do 576 minus 324, I get 252 equals 36R. And when I divide by 36, I get a radius of 7. And in all honesty, ones like number 6, these are as hard as these are going to get. You really just have to remember that when you have something like the R plus 18, that you have to FOIL that. You can't distribute the square. You always have to FOIL. If there's a plus or a minus sign in between and you distribute, you're going to get the wrong answer every time. So you always want to make sure that you're FOILing things like that out. And then after that, your squared terms, 9 times out of 10 are going to cancel out. So it's just solving a regular equation. In number 7, points M and N are points of tangency, and they want you to solve for x. So we know that these would form right angles, and we know that when points of tangency meet at the same point outside the circle, that those two tangents have to be equal to each other. So x squared has to equal 9. And if we take the square root to undo our square, we're going to get a value of 3. Now, helpful hint from Algebra 1 that you might not remember, when you take the square root of a number, it always has two answers, a positive and a negative. So really, this would be both the positive and the negative of 3, because 3 times 3 is 9, but negative 3 times negative 3 is also 9. So when we take the square root of 9, we get both that positive and that negative. Now here's the thing. You can't have a negative side length. So if you have to take the square root, and that negative is going to give you a negative side length, like if this were just x and not x squared, we wouldn't want the negative 3 because we wouldn't be able to have a length of negative 3. But since it's x squared, we know, well, negative 3 squared is going to be positive 9, and 3 squared is going to be positive 9. So either one of those values for x will work. That won't happen a lot. It's just something to be careful of on your homework. If you have something similar to that and you get positive 3 and it tells you you're wrong, try adding the negative 3 in there with it. So that's it for this first section. Let me know if you need anything. Shoot me an email, get on Google Meet if you get stuck. But I think you guys will do pretty well with this first section.